This is a representation of a hypercube, a cube that has expanded into the fourth dimension. Scientists like Carl Sagan have said we can't truly visualize a hypercube because we're trapped in three dimensions. But what if that's not the case? Many years earlier, Albert Einstein and Hermann Minkowski gave us spacetime, saying time is the fourth dimension. The extra lines connecting the two cubes of a hypercube are taught to represent a fourth spatial axis, a direction at right angles to the three we know familiarly as length, width, and height. Charles Howard Hinton popularized this view in the late 1800s, and it remains the standard way mathematicians describe the hypercube today. But what if we combine both ideas? What if we treat these edges not as coming from a new static spatial direction, but as an axis through both space and time? To do that, we can imagine one cube at one place in time and the other cube as that same cube at another place in time. The 4D edges are then better conceived as representing the process of the cube between those two states, not some abstract higher space. Suddenly, the tesseract becomes a map of a cube between the two states, representing a very natural dimensional step from the static 3D form of an object, its motion. This is another depiction of a tesseract, or hypercube, described as two cubes facing each other with all vertices connected by new 4D edges. Instead of the expansion and contraction motion of the last example, this hypercube can represent simple positional motion from one space and time to another. This is a representation of a 4D object that is based on a tetrahedron instead of a cube. The progression from a square to a cube to a hypercube follows a pattern of symmetry, expanding or moving all parts equally. But this object, known as a pentatope, follows a different pattern, one of minimalism. Starting with a 2D triangle, one vertex is pulled up to form the 3D tetrahedron, and from there, geometers have speculated the pentatope to be the representation of an unimaginable 4D spatial progression of a tetrahedron. Translating this object through a spacetime axis of motion, we can continue a minimal progression and move just one vertex of the tetrahedron down into the center. The path it traces reveals the pentatope to be a 3D spacetime map of motion, just like the two hypercubes. In all examples, there is a common structure, an initial state, an end state, and the vertices in between that can represent a path of motion, all aligned with long-established 4D geometry. The math of these 4D objects is sound and undisputed, but the conceptual understanding of a static fourth spatial axis, still taught about today, has had obvious barriers. With this new perspective, is it time for a change? Thank you for watching.